All right, today we're going to tackle a concept from math that sounds, a little intimidating. Uniform continuity. But what if I told you it's actually super intuitive? It's really just about the difference between a bumpy, unpredictable road and one that's perfectly smooth. Let's dive in.
So let's just start with a really simple question. In math, you always hear people talking about functions being well-behaved. What does that even mean? How do we put our finger on what makes a function predictable without any crazy, wild jumps or surprises?
Okay, to really get a handle on this, we're going to use an analogy for the whole explainer. Picture two roads. Over here, we've got the predictable road. It's smooth, it's straight, you can just pick one safe speed and cruise. But over on the other side, you've got the bumpy road. It is full of surprises. You're constantly having to slam on the brakes, adjust your speed, it's a mess. Just keep these two roads in your head.
Seriously, this tale of two roads is pretty much the key to understanding everything we're talking about today. It's amazing what a simple roadmap can teach us about some pretty deep math.
Think about it like this. A well-behaved function is one you could actually sketch out pretty smoothly. You're drawing the graph, and your pencil just glides along. You don't have to make these frantic, tiny little corrections just to stay on the line. It's stable. It's predictable.
And that idea of smoothness brings us right to the main event, the big showdown. On one side, we have just plain old continuity. That's our bumpy road. And on the other, we have the star of our show, uniform continuity, our nice, predictable road. And here is the absolute crucial difference. A function that's just continuous is drivable. Yeah, you're not going to fall off a cliff. But in its bumpiest sections, you might have to slow down to a total crawl to stay safe. Uniform continuity gives you a way stronger promise. It says, hey, you can find one safe speed, a single step size that's going to work absolutely everywhere, from the flat, easy parts to the craziest hairpin turns. So that one word, uniform, that's the whole ballgame. That's what makes this idea so powerful. It's a guarantee. But a guarantee of what, exactly?
So what is this special promise? What is the uniform guarantee all about?
Here it is. The uniform guarantee is a single, one-size-fits-all safe step. It's one fixed amount of wiggle room that is absolutely guaranteed to work across the entire road, not just in the easy parts, everywhere. I just love thinking about it this way. Regular continuity is kind of nervous. It's like, okay, over here you need to be careful, but then, whoa, over there you need to be really, really careful. But uniform continuity just leans back and says, nah, don't worry about it. I can give you one fixed wiggle room that works globally. You're good. It's a global promise, not just a bunch of local warnings. And this isn't just some abstract game that mathematicians play. This pattern of global predictability, it shows up all over the place in the real world. So let's step away from the road for a second and look at a simple metal rod.
Okay, picture a plain old metal rod. The laws of physics, right? They tell us that heat diffuses smoothly. So if you pick any 2 points on that rod, they're super close together, their temperatures are also going to be super close together. You're not going to find any magical microscopic spots where the temperature suddenly spikes by 1,000 degrees. Physics itself gives us a uniform guarantee of smoothness. It's a perfect real-world example of this idea.
So let's bring this back into the language of math really quickly. Step 1, you decide how precise you want to be. Step 2, the function hands you back one and only one safe step size. And step 3, this is the magic part, that single step size works everywhere on the graph. One rule for the whole road. It's that simple. But there is one final, really crucial twist to this whole story. It turns out that whether a road is bumpy or predictable can depend entirely on how much of the road you're actually looking at. The boundaries, the context, it's everything.
Let's just take a classic function that everybody knows. F of x equals x squared. It's just a nice, simple, smooth parabola. So, is it our predictable road, or is it the bumpy road? And the answer is, it depends, which is so cool. If you only look at the function on a small, bounded road, say from 0 to 1, the curve is gentle. It's totally tame and predictable. It's uniformly continuous. But now look at that exact same function across an infinite road, all real numbers. The curve gets infinitely steep. A tiny little step way out there sends the values soaring. There is no longer one single safe speed that works everywhere. The same function is suddenly not uniformly continuous anymore.
So here is the huge takeaway. The road you are on, the domain, can actually be more important than the car you are driving, the function. The very same car can feel perfectly safe on a closed, predictable track, but become completely unmanageable on an infinite highway that gets steeper and steeper forever.
And that really just leaves us with one final thought to chew on.
This pattern, it's not just in math. Where else do we see this? Systems in science, in economics, maybe even in our own lives, that seem totally well-behaved and predictable when you look at them up close, but then go completely wild and unpredictable when you zoom out and look at the global picture? It's a really powerful idea to think about. Thanks for joining me.